You've probably heard of the Pythagorean theorem, which states that a squared plus b squared is equal to c squared for any positive integers a, b, and c. But does a cubed plus b cubed equal c cubed? What about a to the fourth plus b to the fourth? Does that equal c to the fourth? This is where things get a little bit messy. Welcome to Fermat's last theorem, which states that a to the n plus b to the n equals c to the n has no possible solutions for any positive integers a, b, and c, and any positive integer n greater than 2. Seems pretty simple, right? Well, not really. For centuries, this simple equation had mystified the world's most brilliant minds. From the day it was conjectured in 1637 all the way until 1995, this problem went unsolved. And there wasn't any real progress on cracking Fermat's last theorem until 1955, when two Japanese mathematicians, Shimura and Taniyama, believed that two seemingly unrelated things, rational elliptic curves in modular forms, had a one-to-one correspondence, known back then as the Taniyama-Shimura conjecture. What are elliptic curves? Elliptic curves are, well, curves on an algebraic plane, simply described by the equation y squared equals x cubed plus ax plus b. Any choice of a or b results in a different elliptic curve. They're probably most notable for being used in elliptic curve cryptography, but that's another topic for another day. What are modular forms? Modular forms are, to put it simply, a group of functions on the complex plane. These functions are characterized by being oddly symmetric. They're used in all sorts of contemporary branches of math, but explaining them any further is out of the scope of a 5-minute video on Fermat's last theorem. On its own, the conjecture has nothing to do with Fermat's last theorem. However, in the 80s, a mathematician named Jean-Pierre Serre tried to prove that when solutions for a, b, and n, in reference to Fermat's equation, were associated with an elliptic curve, written y squared equals x times x minus a to the n times x plus b to the n, the resulting curve, known as the Frey curve, was not modular. He was unable to do this on his own, however. Another mathematician, Ken Ribbit, was able to prove that it was not modular. The implications of this were huge, as if you prove Taniyama-Shimura, you prove Fermat's last theorem, and vice versa. And in 1993, Andrew Wiles did exactly that. Actually, let me rephrase that. Andrew Wiles tried that, and failed. After sending his proof in for a peer review to Nick Katz, a colleague of his, Nick found a major error in his proof. After fixing the errors in his earlier proof in 1995, Andrew Wiles had finally proven Fermat's last theorem. So where does that leave us today? Are there any other hard unsolved problems out there? Well, there aren't any on the scale of Fermat's last theorem. There are still many unsolved conjectures out there. An interesting one I found while researching this video was the Birch and Swinnerton-Dyer conjecture, which has a $1 million prize awaiting the first person to provide a correct proof. This conjecture deals with certain equations that define elliptic curves over the rational numbers. In fact, Andrew Wiles himself formally stated the conjecture, which proposes that there is a simple way to tell whether these equations have a finite or infinite number of rational solutions. Want to get started on solving it? The problem's all yours. So far, there's only been progress in specialized cases, but if you have a strong background in number theory and a good understanding of elliptic curves and group theory and a few other fields of math, then you can... this is much harder than it seems. Obviously, there's still a lot more to be known about this problem, which is regarded as one of the most challenging in all of mathematics, but it's just one example. You don't need to have some kind of innate gift to solve these problems. You don't need like a fancy degree or anything. You just need to be able to think outside the box, like Taniyama and Shimura did, like Ken Ribbit and Jean-Pierre Serre did, like Andrew Wiles did. Thanks for watching. Hope you enjoyed.